Start, sir.
Good morning, students. Welcome back to our webinar classes. Physics. We are at chapter 6, chapter 9, that is electromagnetic induction. Okay, so I hope you understood chapter 8 very well. So we are moving on to a very important chapter and easy to understand. Concept is very important. So that is electromagnetic induction. Okay, so let's move in. Right here, some introductory part to be discussed, that what we learned in the previous chapters. So if you look at this diagram, one circuit is kept out here, the circuit is here, under that a magnetic needle is freely suspended. Now, if you observe this circuit, here is the battery is connected, positive and negative, right? So the moment the switch is on, then the current flows through the circuit. Yes. Now, near that current carrying conductor, we kept one magnetic needle. So initially, the magnetic needle was aligned in the north and south directions, but the moment when the switch is on, so that the current is flowing through the circuit, and if you observe, this needle is deflected towards the west direction. And similarly, if you change the battery terminals, then the direction of current is changed, and deflection of magnetic needle is also changed towards east direction. So this already we have learned in the experiment, Oersted experiment. Okay, so according to Oersted and Ampere, the current carrying conductor generates magnetic field. See, observe this. This needle reflects only when nearby any magnetic field is there, then only it shows deflection. Yes, that we know that whenever the two magnets are kept closer, means if they are like poles, they will repel. If they are unlike poles, they will attract. That we know. So, as per the situation, either deflection means either attraction or repulsion depends on the neighboring magnetic field. Okay, so here this needle is deflecting because nearby some magnetic field is there. So this magnetic field is generated due to the current which is flowing through the circuit. I am repeating, whenever a current carrying conductor means the current which is flowing through the conductor, we know perpendicular to that the magnetic field also generates. This point is to be understood. Whenever a conductor carries current, then perpendicular to that magnetic field will be generated. So due to this magnetic field, nearby we kept one magnetic needle that is showing deflection. Okay, so it is showing deflection because of the magnetic field is generated due to the current in the conductor. This point is to be understood. Then only we can understand the concept. Right? So I am repeating, due to the current which is flowing through the circuit or conductor, magnetic field will be generated. And due to that magnetic field, this magnetic needle shows deflection. Okay, this was explained by Oersted and Ampere, and we studied Oersted experiment also. So according to Oersted and Ampere, the current carrying conductor generates magnetic field. Okay, current carrying conductor generates magnetic field. Now, we know both electricity and magnetism are interrelated. Both electricity and magnetism are interrelated. And they found that moving charge produces magnetic field. So this point is to be understood that here moving charge produces magnetic field means moving charge produces electricity. Moving charge produces electricity. And perpendicular to that, the magnetic field is generated. So magnetic field is generated because of the motion of the charge part, motion of the charge. Okay, so now see what you understood here means we are going deep into the concept that here because of the charge is moving, means if the charge is under motion, then only the magnetic field is generated. The charge is under motion, then only the magnetic field is generated. Now the question is, if the magnet is kept under motion, can it produce current? This is the question. Okay, so what is the concept? Moving the charge produces magnetic field, then vice versa. If the magnetic field is changed, means if the magnets are moving, then can they produce current? This is the question. Okay, so this is the key topic that we are discussing in this chapter, that is electromagnetic induction. I am repeating, when the charges under motion, they will produce magnetic field. Now the question is, can moving magnets produce current? This is the topic. Okay, so can moving magnets produce current? Yeah, so we stress on this point that can the moving magnets produce the current? Yes. Okay, so now we are moving into the concept here. So yes, according to Michael Faraday, the scientist, and Joseph Henry, okay, Faraday and Henry, in the year 1830, experimentally demonstrated that changing the magnetic fields induces the current in the closed circular coils. Okay, so this is the concept, means this is the experimental support that changing magnetic fields or magnets which are under motion. Okay, changing magnetic field or magnets which are under motion induce, means produce or create, okay, generates, induce the current in the closed circular loops, circular coils. And circular coils are nothing but conductors which are in the circulation, conductors which are in the circulation. So when the coils are kept in such a way that the magnets are under motion. Okay, when the magnets are under motion, then in the circular coil, the current will be induced. This was experimentally demonstrated by the two scientists, Faraday and Henry, in the year 1830. Okay, and repeating, changing the magnetic fields induce the current in the closed circular coils. Okay, closed circular conductors or coils, right? Okay, so with this, with these two scientists, what we understood that yes, moving magnets can produce the current. Moving magnets can produce the current. So now we are moving. So in this chapter, we study methods on changing the magnetic fields and its applications. Okay, so in this complete chapter, what we are discussing here, what are the equations, what are the laws and phenomena which are involved in this chapter, and also some part of application also we are discussing. Okay, some part of application like generators and transformers, eddy currents, all these are some type of applications that we are going to discuss at the end of this chapter. And during the chapter, we are discussing the laws, which are involved in these concepts. Okay, so in this chapter, we study methods of changing the magnetic fields. Okay, so how to change the magnetic fields to get the induced current. So we will see that. Okay, so in this complete chapter, we discuss the methods and few laws involved in this and few applications involved in this chapter. Okay, so next point is the phenomena in which the induced electric current. The phenomena in which the induced current is generated due to the change in magnetic field is called electromagnetic induction. So this is actual statement of electromagnetic induction. Okay. Okay, induction means what? It's a forcibly creating like. So the phenomena in which the induced electric current. Okay, so this electric current is just like that, it is not coming to the picture, just it is induced. Okay, forcibly it is created. So induced electric current is generated due to change in magnetic field. So here in this chapter, we are changing the magnetic field. We are changing the magnetic field continuously, which is kept near the coil. Then inside the coil, the current will be generated. Current will be generated. So this whole phenomenon is called electromagnetic induction. Electromagnetic induction. Okay, so electric field or electricity is generated due to the magnetic field. So here is the concept electromagnetic induction. Okay, so now we move on to the next is very foremost important basic definition that is to be understood here is magnetic flux. Already discussed in the last class what is magnetic flux, that I have given that number of lines of force which are passing through, that we discussed in the magnetism concept, magnetism and matter concept. There we discussed magnetic flux means what? Number of lines which are coming from the magnet. The number of lines which are coming from the magnet, which are passing per a cross section, some area. That is what is a magnetic flux that we discussed in the last class. So this last chapter. Now here is the magnetic flux same definition. The amount of magnetic field is linked with the surface area. I am repeating, amount of magnetic field is linked with the surface area. Means consider any material, iron or something like that, okay? Any magnetic material like iron, cobalt, nickel, now kept in the magnetic field. Okay, keep that piece in the magnetic field. Then the magnetic lines of force which are coming from the source. What is source here? Magnet. So from the magnet, all the field lines comes out and enters into the iron piece. We kept the field. So how many lines of force are entering into the piece of iron? That is nothing but magnetic flux. Okay, in a given surface area, how many lines of force are entering into that? So that is called amount of magnetic field or number of lines of force which are entering into the surface area. So here is, that is the magnetic flux, that indicates with the pi here, denotes with the pi here. And it is expressed as a, look at this expression, pi b. So pi suffix b. Pi is the magnetic, pi is the flux, and b is the magnetic flux. And in electron, in the electricity concept, that we know that pi e indicates the e here. Suffix e means what? Electric flux. And here it is b indicated. B means it is a magnetic flux. E is equal to b dot a means b a. Here b is multiplied with the area. Here B is what? Is the magnetic field lines. Magnetic field lines which are passing through a area of cross section. That is what B is. Or simply dimensional. Magnitude wise, you can write in the other form that say is a BA cos theta. Okay, BA cos theta. And here the theta is the angle between the magnetic field and the surface area of the plane. Okay, look at this diagram that you can understand here. So here is any material, okay, any material, right? Any material is kept in the external magnetic field, kept in the external magnetic field. So lines of force, green color is the lines of force indicated with B here. Okay, whose the surface area, this N is indicated with there, what is it indicates the direction, okay, unit vector direction. Okay, so this plane is exactly perpendicular, okay, to the magnetic field, right? So number of lines of force which are passing through this surface area. So this is apt for the definition. Okay, the amount of magnetic field is linked with the surface area. So this is what is the definition. Okay, represented with the diagram here. Now if you see the next diagram, see just here is a variation, means amount of lines of force which are passing through the surface. Variation is, it is shown here. See this plane now is a parallel to the magnetic field direction. Okay, right? So here plane direction is perpendicular to this. Okay, surface is parallel and the plane is perpendicular to the plane is parallel to the magnetic field and surface is perpendicular to the magnetic field. Okay, so here here the zero flux is showing zero flux. And see, look at this. Now, just this over the plane is tilted with a certain angle theta. Plane is tilted with a certain angle theta. Then our equation becomes this magnetic flux. Equation becomes Ba cos theta. So this angle, this plane is making some angle. Okay. So this is n is what is the surface direction. Okay. Right. So this is about magnetic flux. So this is very important equation that we will use in various places in the next discussions. Okay, very important role is going to play here, and it is a scalar quantity. It has only the magnet, and it is a Weber or Tesla meter square. So it's a unit to measure this magnetic flux. It's a Weber or Tesla meter square is a unit to measure the magnetic flux. Okay, so this is about magnetic flux. This is a very introductory part. Okay, now the same magnetic flux, if we use that in irregular shape. Okay, in the previous diagram that we have seen in a perfect shape, perfect surface here. Now it is irregular shape. For any irregular surfaces, how to identify the magnetic flux, amount of magnetic flux which is flowing through the surface. Even you have observed the magnetic field is also not uniform. Okay, observe. See, in this diagram, magnetic field is uniform, means all the lines of force are uniform, moving in the same direction, and the plane is also perfectly shaped. And if you observe this, surface is irregular, and in this diagram if you see magnetic field is also non-uniform, means it is not moving in the same direction, moving in different directions. This is non-uniform magnetic field and irregular shape, irregular surface. For such situations, how to identify the amount of magnetic flux, magnetic field which is passing through. Okay, so for irregular surfaces, we have to integrate each and every position to get the whole magnetic flux present in the closed surface. Here, what is that? We need to integrate. So for that, what we have to do is, at any point on the surface, assume a small surface area. At any point on the surface, because the surface is not perfectly shaped, it's not a perfect shape. So that's why we need to consider perfect shapes, means number of position, number of perfect shapes. If we assume, then all the surface areas, are summed, means added together. Is nothing to integrate. Means all are added, then finally you can get the total amount of magnetic flux which is passing through in irregular surface. Okay, so for irregular surface area, what we have to do? We need to assume a small portions, okay, small surface areas on the total surface, and integrate them. Individually, we need to identify the amount of flux which is coming out from the surface and add that. Then we can get the total flux which is coming out through the irregular surface. So here, so we need to integrate now. So that's why magnetic flux is product of average magnetic field and the perpendicular area that is penetrates. Yeah. Understood this point? So the magnetic flux is the product of average magnetic field. Why average? Because this either magnetic field is not uniform or the surface is not perfect. Means it is an irregular shape. So that's why what we have to do, we need to identify, we need to get a small perfectly shaped surface areas. Those are called dA. dA. A is the area. For small surface area, we indicate that as a dB. Okay, and so automatically we get dB also, d pi also. We will get a d pi. Because d pi, only pi means what? Only pi is the magnetic flux of the total. But here we are integrating for individuals. Okay, for a small dA, we will get the small d pi. Means for a small surface area, very few lines of force will enter. Okay, very few lines of force are entered per a small ds. Small ds are dA surface. Okay, so how much magnetic field you get? D pi. What is d pi? A small magnetic flux. A small magnetic flux. Understood? For a total surface area, you are getting total magnetic flux, and for the small surface area, you will get a small magnetic field. Okay, for total A, capital A, you are getting total pi, and for a small dA, you are getting small d pi. Okay, that's what is an expression here. Okay, so magnetic flux is it's simply the product of magnetic field, that is average magnetic field, because we are considering the irregular surface and non-uniform magnetic field. Then it will become average. Means at all the points the same magnetic field will not be present because it is a non-uniform. Okay, and so it is the product of area of cross section. So then sum of all these means integrating those individual surface areas, and you get here is the expression that pi is equal to integral b dot dA. So here B is a magnetic field, okay, and dA is the small area, okay, small area, right? So here from this you can take out B value to get the magnetic field density. Yeah, he has given magnetic field density. The density that you know is the mass per unit volume that you know. So here mass is nothing but the number of lines of force. Mass is nothing but amount of magnetic lines of force coming per unit area. Yeah, is given. B is equal to d pi by dA. So here you can see that d pi. I told you d pi is a magnetic flux, a small magnetic flux due to the small surface. Okay, use the identify the terminology here. So B is the magnetic field present in that surface area is equal to d pi by dA. Okay, d pi by dA. See, if you observe, it is a d by dA. d by dA means with the change of area. With the change of area, okay, with the respect to change of area, flux is changing, then automatically the amount of magnetic field also changes. Okay, so this is about the magnetic flux, and you understood the two equations. One is for a perfect surface, and another one is the irregular surface or non-uniform magnetic field. Okay, right. So as we discussed that how the electromagnetic induction is produced, that we discussed in the introduction area, that whenever the change in magnetic field is there at the conductor, means or a coil, then what happens? Current will be induced. We discussed that there are so many experiments demonstrated by Faraday and Henry. So among that, as per our syllabus, we'll discuss three situations. In three cases, we'll discuss. Okay. So three cases. In these three cases, if you understood well, then the coming applications that you can understand easily. Right. So here, to understand the concept of electromagnetic induction, okay, they performed a series of experiments. Faraday and Henry was that experimentally demonstrated to create the induced current by changing the magnetic field. Okay, so among them we basically we have three experiments. So they are first we'll start with this. Okay, so here look at this. The current carrying coil is held stationary connected to the galvanometer. See, we are discussing the first experiment to identify how the electromagnetic induction will be generated. Okay, we are entering for the experimental discussion that first one, the first demonstration, very important. Try to observe keenly. Okay, so here, look at this. The current carrying coil is held stationary. Look at this circuit. Held stationary. Okay, so this is the coil is indicated with C1. Okay, and both the ends are connected to the galvanometer. Both the ends are connected to the galvanometer. Okay, and this is kept stationary. This is kept stationary. Now, the bar magnet is kept under motion near the coil. Okay, this coil is connected to the galvanometer. Observe that. Now, what is the function of galvanometer? Galvanometer shows the direction of flow of current through the coil. Okay, galvanometer shows the direction of current in the coil. So it shows deflection means from the zero, right side and left side it will move like this. Okay, if there is no current, the needle is exactly at the center. If the current is flowing, then either this or this direction it will indicate. So as per the direction of current, positive, negative, like. Okay, so this is equilibrium, means there is no power, there is no current which is flowing. Then it is moves like this. If means it shows only the direction, it won't measure the amount of this one. Okay, it's only the direction. Now ammeter is the measures the amount of current which is flowing through the circuit. It shows the deflection here. It shows the direction. Okay, so the bar magnet is kept under the motion near the coil. Yes. So look at this diagram. This is the bar magnet, and this under motion. This is kept under motion. This is moving towards. It is moving towards the coil. Look at this diagram. The coil is no way connected to any external battery. Okay, there is no external power supply to this coil. Okay, just it is connected to the galvanometer only. Now, yeah, it is kept in stationary, and now this magnet, bar magnet, is moving towards the coil. It is approaching towards the coil. See, this dotted line is the axial line, axis. Okay, and this is moving towards the coil. Okay, then what happens? See, moving towards the coil means what we are doing here. Number of lines of force which are coming out from this north pole. Okay, the number of lines of force means what? Magnetic field or magnetic flux. Okay, the magnetic flux is changing. Means while this magnet is very far, if the magnet is very far, then what happens? Number of lines of force which are passing through the coil will be small or very less. Understood? When the same bar magnet is moving towards the coil, then more number of lines of force will enter into the coil. Remember, we are discussing magnetic flux concept. What is magnetic flux? Number of lines of force passing per unit area. Yeah, that's what here. The magnet, bar magnet, when it is very far, then the few very small lines of force will enter into the coil. And it is coming closer to the coil, more number of lines of force will enter into the coil. So what we are doing, we are changing the magnetic field. Yes or no? We are changing the magnetic field continuously. We are changing the magnetic field continuously. So this is what we are doing, changing the magnetic field. Changing the magnetic field. So just like that, for changing the magnetic field, how the current will be generated? Here the concept is conductor means what? It is a full of free electrons. Conductor means what? It is a full of free electrons. And at the normal situation, all the free electrons will move in a random direction, different directions. So then the charges are moving in the random directions, then the net current will be zero. Net current will be zero. Even though they are moving, they are not, of course, they are producing the current, but they are not moving in particular direction. They are moving in a random direction. Then the net current is generated due to the motion of random motion of charge carriers is zero. Okay, electrons is zero. So here, now what we are doing, by keep on changing the magnetic field, means keeping the magnet, it's a field, it's a force, okay, lines of force. When the magnet is getting towards the coil is nothing but conductor is nothing but full of free electrons. Now those free electrons, motion is restricted to move in a particular direction because of this magnet. Because of this magnetic field or magnetic lines of force. So due to this magnetic force, those electrons in the conductor are aligned to move in a particular direction. Aligned to move in a particular direction. Then what happens if all the electrons are moved in a particular direction? So automatically the current will be generated. So this is the concept involved here. Okay, this is the concept involved here, that when the force is applied to the conductor, which force it is? Magnetic force. Okay, that is lines of force. Applied to is kept near the coil, then the electrons are aligned to move in a particular direction, then the current will be produced, and this, yeah, so that's what, because of that current, the current shows deflection. So what we have done here, due to the change in magnetic field, current is generated, current is induced, and this current is called induced current. This is what our concept, electromagnetic induction. Now, experimentally proved means experimental values here. Look at this, the same diagram here. Now we need to observe some situations here. It's a very key pointer. Okay, observe some situations here. Look at this. There's a magnet who is moving towards the current is connected like this. The same diagram here. Now position the magnet and current in the coil. How they are changing. Look at this. So with this point, you can understand well. Once it is understood, then whole chapter is that easy. That easy. Just like that you can understand. So here position of the magnet. Observe this. Stationary. When the magnet is kept constant. Now tell me, when the magnet is kept constant, number of lines of force which are coming out from the north pole or magnet will be the same, no? Constant number of lines of force will enter into the coil. Yes, sir. If the magnet is kept constant, stationary, then the number of lines of force which are entering into the coil will be fixed. Fixed number of lines of force will be there. So, fixed number of lines of force are moving means there is no change in magnetic field. Yes, sir. The fixed amount of lines of force are moving means there is no change. So, what we observe, when the position of the magnet is stationary, then the current in the coil means the galvanometer deflection is zero. Galvanometer deflection is zero. So, current in the coil is zero. Why? Because the magnetic field is not changing. Magnetic field is not changing. What is the condition? What is the Faraday's and Henry explanations were? What? Changing magnetic field induces the electric current in the coil. That point is to understand. What were this Henry and Faraday explained in their demonstration, experimental demonstration was what? Changing magnetic field induces the electric current, okay, in the coil. So this point. So as per this point, see, look at this. The magnet is kept constant. Then, of course, the lines of force comes out. But in the coil, how many lines of force will enter in? Only fixed number. So this is not changing. So due to not changing, due to the bar magnet is kept in the rest position, then what happens? The current which is flowing through the circuit is zero. Okay, and immediately the next point. Making means moving this magnet towards moving this magnet towards the coil. Yeah, look at this. Towards the coil. So what you observe, the bar magnet is in motion. bar magnet is under motion. Then this galvanometer shows deflection. Once it is shown deflection means what? The current which is flowing through the circuit coil. So it shows deflection I here. Okay, it is showing deflection means what? Current is flowing through the coil. So it produces some I here. Understood? So I am repeating, towards the coil. If the magnet is moving towards the coil, C means what? It's moving towards the coil means what? Number of lines of force changing continuously. Changing continuously, then what is that? The current is produced in the coil and the galvanometer shows deflection, and so we can conclude that current is produced, current is generated in the coil. And similarly, and keeping that magnet towards, means moving towards the coil cathode, very near. Okay, keeping that magnet very near to the coil. Okay, stop at the coil. Stop at the coil, near the coil. Then what happens? When whether it is near or far, when it is the magnet is stationary, then lines of force which are coming out from the magnet will be fixed. Means fixed amount of lines of force will enter, even though magnet is very near to the coil. Even though magnet is very near to the coil, only fixed number of lines of force will pass through. There is no change. So when there is no change, then the no current passes through the coil and there will be no deflection in the galvanometer. Then we can say that the zero current is flowing through the circuit. Okay, see the third one is the stop at the coil, then the current in the coil is zero. Okay, similarly, now the magnet is near to the coil now we are moving that backward. So moving that away from the coil. Okay, so away from the coil. So moving, dragging backward, so moving backward now. Okay, so observe that the magnet is under motion in this case, moving backward, then the number of lines of force changes from previous position to the present position. So magnetic field is changing, lines of force which are entering into the coil will change. Okay, so due to that change also, again the current will be generated and the deflection shows exactly opposite to the previous situation. What is the previous situation? The magnet is moving towards, and what is the present situation? Magnet is coming backward. So the magnet galvanometer deflection shows previous case in one direction, in the present case in the opposite direction. I told you the function of galvanometer. Okay, so it shows only the direction. So in maybe look at this diagram. Maybe in the first case it is moving anti-clockwise, and the second case moving in the clockwise direction. Okay, it shows only the direction. So those direction part we discuss in the next concept. Okay, very important. How to identify the direction, that is very important. Okay, so here just we are discussing the concept here, it's electromagnetic induction concept we are discussing here, and direction and polarity that we'll discuss definitely in the immediately the next class. Okay, so here the galvanometer shows only the direction, that is whether it's a positive or negative direction, clockwise and anti-clockwise direction. So here now we'll move to the next point is the stop at anywhere. Okay, you move that magnet, moving away from the magnet and stop it in between anywhere. Okay, in between at any point, you stop it at a particular point. Then what happens? Again, the magnet is in the rest position. Then, which are coming, means lines of force which are coming from the magnet and entering into the coil will be fixed amount. Will be a fixed amount. So, fixed amount is what? Magnetic field is not changing. But what is the condition? Change in magnetic field should produce the induced current. But here in these cases, see first stationary case, stopped at the coil and stopped at anywhere. In these three cases, the magnet is in the rest. Then the current which is flowing through the coil is zero. But what you understood with this experiment is to produce the current, to induce the current. The magnet should be, or magnetic field should be under changing mode. Okay, the magnetic field should be continuously changing. That may be from small to bigger or from huge to small, that magnetic field continuously should change. Then only the current will be generated. This current is called induced current. This current is called induced current. Okay. So here just some more very clarification for this. Yeah. With this, we can conclude that the current is generated only when the magnet is under motion. Okay, so as per that table that we discussed. So from that table, yeah, what to conclude? The current is generated only when the magnet is under motion. Okay, so it shows that relative motion between the magnet and the coil induces an electric current in the coil. So relative motion. This is what with respect to the coil. Coil kept stationary, no? That is the first one. The coil kept stationary and the magnet is under motion. So with respect to the coil, magnet is under relative motion. With respect to the coil, magnet is under relative motion. Okay, both are in the relative motion. So magnet is coil is kept constant. The magnet is with respect to coil is under motion. So it is a relative motion. So look at this diagram, same diagram here. So magnet is a moving, the arrow indicates to and fro motion, okay? The backward and forward motion, right? So it's a coil is connected to the galvanometer, okay? So while it is coming closer, the galvanometer shows in one direction, and the magnet is moving away from the coil, the magnetic deflection. So galvanometer deflection shows in the other direction, upward directions. Okay, so with this, what we conclude that, what was the conclusion that the current is generated only when the magnet is under motion. Okay, so this part is to be understood. The relative motion between the magnet and the coil induces an electric current in the coil. Okay, yeah. So now we move on to the next experiment. Okay, so what is the next experiment here? The bar magnet is replaced. The bar magnet is replaced. Have you observed? If you understood the first experiment, then it is dead easy to understand. In the first experiment, what were used? One magnet and one coil. Okay, one magnet and one coil used, and the coil is kept stationary. Now, in the second demonstration, the bar magnet is replaced by another coil. The bar magnet is replaced by another coil which is connected to the battery. Observe this diagram. Okay, so the coil 2 is connected to the battery here. Remember, whenever the conductor is connected to the power supply, means a battery, then current will be generated through the conductor. Current flows through the conductor, and the conductor produces the magnetic field. This was explained by Oersted. Oersted experiment was there. We studied Oersted experiment. Okay, according to Oersted experiment, any current carrying conductor can produce the magnetic field. Yes. That's what we are here discussing, that this is the current, this is the conductor, okay, circulated in the shape of coil, and the two ends are connected to the battery. Then the moment battery is switched on, then what happens? The current flows through the circuit, the coil. Then current, once it is generated, then perpendicular to that, the magnetic field will be generated definitely. Yes or no? So this coil, current carrying coil, produces the magnetic field. Simply, this coil too behaves as a magnet. So that's why we replaced magnet into the coil. This is the first point. So the bar magnet is replaced by another coil which is connected to the battery. Okay, and the first coil number 1, C1 is as it is. C1 is as it is, and that is connected to the galvanometer. It is kept stationary. Now this one is, we are taking another coil 2 which is connected to the battery. Then due to that battery, the current flows through, and perpendicular to that, the magnetic field will be generated. So this is one. Now look at this. When the battery is on, current flows through the coil 2, so that magnetic field develops. Okay, that right? Now the coil 2 acts as a bar magnet. The coil 2 acts as a bar magnet, that everybody should know that whenever the current is passing perpendicular to that, the magnetic field will be generated. Okay, so any current carrying conductor can behave as a magnet. Okay, that's what. So coil 2 acts as a bar magnet. Now coil 1 is kept stationary and the coil 2 is allowed to move towards the coil. So same performance as we done in the experiment 1 can be done here in the experiment 2. Okay, so allowed to move towards the coil 1 and the galvanometer shows deflection. I told you, so simply in the place of bar magnet, we get the coil 2 here, it is connected to the battery. So this coil 2 behaves as a bar magnet. Now the same, what we have done, the experiment 1, the same we do here, that bar magnet we used to move in the first experiment, and now we are making it move with this coil 2. Okay, now we are making it move with this coil 2. Now look at this. So allowed to move towards the coil 1, and the galvanometer shows deflection. Same procedure, same experiment, but just we replace the magnet. Okay, so similarly, if the magnet is moved backward, then the galvanometer shows deflection in the reverse direction. Yes, whatever we observe in the experiment 1, the same is we are observing in the experiment 2. Okay, because the coil 2 is behaves as a magnet, the same performance. Okay, now here also the coil 2, if it is in the rest, coil 2 which is connected to the battery, if it is in the rest, then there will be no deflection in the galvanometer. If it is a rest means what? There is no flux, it is constant flux which is entering into the coil 1, constant flux is entering into the coil 1. So if it is a constant, then there will be no change in the deflection, there will be no question of producing a current. Only thing is coil 2 should be under motion. That may be towards or away, but it should be under motion. If it is the rest, there will be no deflection, there will be no current. So that's what we learned in the second experiment. Okay, now the same. When the coil 2 is kept stationary, then there is no deflection in the galvanometer. Okay, so the deflection shows one direction. Okay, if it is moving towards, and deflection shows in the other direction if it is moving away, and if it is a rest, then it shows no deflection. So again, it is relative motion between the two coils induces an electric current. The same concept. So again, with respect to C1, C2 is under motion. With respect to C1, C2 is under motion. So relative motion between the two coils induces an electric current.
That conclude the session, sir.
Right. So with this, we'll stop here, and we have another experiment to discuss this electromagnetic induction, how it is produced. Okay, so with this, we'll stop this session, and in the next class, we'll continue this. Okay, thank you.
Thank you, sir.